So, welcome to our online audience. Let me introduce myself. My name is Nasir Manan. I'm the principal engineer for the Advanced Design Automation Metrology lab here at CCAT. My background is mechanical and software engineering. I have been with CCAT for about 16 years. Um, I do, I know the supply base quite well, at least in this particular area. For those of you that I have not met yet or had the chance or had the pleasure to tour your facilities or know about your business, please do reach out to me. I do look forward to working with you. Again, CCAT is an organization that does have funding from the state and the federal government to help the supply base advance in the technologies that you use. So with that, we do have for our agenda today, digital thread for Naval Maritime. It is more of a high level presentation, a set of presentations. And then we do have a lunch and learn and then a demonstration that's going to happen over by the additive flex cell when you were touring the Atom Lab side with one of our technology partners back there. So I'd like to ask, is Ron here? So I'd like to acknowledge, again, Eileen Candles, who is our online host. If any participant online has any questions at any time, please do use the questions portion of the Zoom meeting to put in your questions, and then we will ask those at the end to the panel that's going to stand up here. I'd like to introduce our CTO, Jackie Garofano. She's going to introduce a little bit more about CCAT and what we do.
Thanks, Nasir. Again, welcome everyone. And for those tuning in virtually or also on demand. So we like to be able to have our programs in perpetuity. So there hopefully will be some viewership. I am probably stepping in for Ron Angelo, who many of you here in-house had met earlier this morning. Welcome again to CCAT. Our vision really is to provide transformative solutions for the broader industrial base all across the country. Although Connecticut is in our name and we focus very much in our state and regionally across the Northeast, we like to say we're available to companies from Connecticut to California. So thanks for those that are CCAT has been in existence for nearly 2 decades, and since our inception, we have always really focused on the advancement of applied technologies. So for those that are here in person, you had the opportunity to tour through our facility and see that in action. We also are very proud of the fact that we are powering and also empowering the workforce of the future. So although we won't necessarily get to that in our program today, if you have any workforce needs that we can help you with, happy to talk to you afterwards. So as an applied technology demonstration and training center, what our team does is to truly work to develop and validate and demonstrate these solutions that companies will need. So what we like to say is we provide turnkey solutions. We take this in-house with applied R&D with our phenomenal team here, and really then push that tech transfer and adoption into the supply base. So what is not co-located here is our Advanced Composites Technology Center, which is a public-private partnership with Pratt & Whitney that's been stood up for several years now. And we have a team there that's working with Pratt, the advancement of commercial turbine engines. So doing composite layups, complex 3D geometries, very exciting work. I'm proud to say that CCAT is members of 4 of the 16 Manufacturing USA institutes that are funded through the Department of Defense, like ARM, the Advanced Robotics Institute, MXD, the Digital Manufacturing Institute, as well as America Makes, which is all focused in additive manufacturing. And CCAT, we've been in that space of additive for more than a decade. SESME, the Smart Manufacturing Institute, is funded through the Department of Energy. Nasir and colleagues have worked on technical projects with partners across the ecosystem on SESME, and very excitedly, we have locked in an award with MXD. So our portfolio here mentioned was, oh, sorry for the difficulties. Of course, you have your CTO talking, and here we are. So anyways, we have a diverse portfolio, and our tech centers, for those that have not seen it in person, we have our advanced design, automation, and metrology side of the house focused on model-based definition, inclusive of digital thread. So for the Naval Maritime population, we'll be digging into that this afternoon. Generative design, both for design for additive as well as what you might need in the digital model-based definition space. Industrial IoT, we have a collection of metrology systems here, and our colleagues are going to speak to you about some of those that are in-house here at CCAT at our tech center. And then additive technologies, I've shared that we've done that for quite some time, and we have a large, diverse portfolio. So there's 7 different families of additive technologies, and here at CCAT, we have 5 plus hybrid. Hybrid allows you to do both additive and subtractive in all-in-one machine. That is our most popular machine. If we had 4 shifts and 5 people working that, that would be phenomenal, but we move ahead. So if hybrid is in your space, or you don't know what hybrid additive is, you're certainly in for a treat. But we're not here to talk about that today. We're here to talk about model-based definition. So, and also digital thread. I'm going to turn it over to you, Nasir, and hope that the mic stays strong. So thanks, everyone.
Great, thank you, Jackie. Again, I'd like to thank Walker Potts for co-hosting this with us, and like to invite him up here to say a few words.
Thank you, Nasir. My name is Walker Potts. For those of you who don't know me, I'm the Executive Director of the Naval Maritime Consortium. What we do is, in our relationship with Electric Boat, our relationship with CCAT, came from the need from particularly Electric Boat, but more broadly the entire submarine industrial base, and the need for greater capabilities and increased capacity to get the submarines built and the componentry built to supply the construction of those submarines throughout the industrial base. And that's not just Connecticut, that's not just New England. It's small to medium manufacturers that are either working currently in the submarine industrial base or pivoting from another defense sector or from a commercial sector to be able to support this work that's of absolute critical national defense interest. So I just want to thank our partners here at CCAT. I think between us, Electric Boat, CCAT, we have a really fantastic team where the processes and the technology that they're validating here can then transition into our member shop floors that can then support Electric Boat and the ambitious production schedules that they have over the next 30 years of submarine construction. So thank you to Nasir. Thank you to Eileen for helping pull this together, and Donna. Thank you very much, Oscar over there, and to Joe and Joel, to Joe, Joel, and Jeff, who I don't see here at the moment. But we've got a phenomenal team here, and for all things related to model-based definition, metrology, additive, CCAT's a fantastic team, and we just can't say enough good things about them. So thank you again, Nasir, for hosting. Appreciate it, and feel free to reach out and follow up with any questions. Thank you all.
Thank you. So let's, at this point, I'm going to jump into my portion of the presentation. And then we're going to be hearing from our technology partners as well, talking more in depth about their particular solutions and how you can streamline your processes using advanced technologies. So to kick this off, let's first ground ourselves with the definition of model-based definition. What does it actually mean? There are some applicable standards that are out there. The ASME Y14.41, that is the Digital Product Definition Data Practices, ISO 16792, and then arguably the most important one for Naval Maritime would be the United States Department of Defense. They released MIL Standard 31,000 Revision B in October 2018 to codify the use of model-based definition as a requirement for technical data packages. This is the type of format that the DoD is going to be releasing. And as a supply base, you want to be ready to be able to consume this kind of data. But when I say consume the data, this is where the crux of my presentation lies. So if we look at kind of the definition of what do we mean by model-based definition? In a visual, you can see on the screen here, we're going from a paper-based, traditional process to a fully digital 3D model-based workflow. So you have, not only do you have the CAD model as your source of truth, in other words, now, you're no longer going to be relying on the 2D drawing as the go-to for the product definition. You're going to be looking at the CAD model with all the embedded PMI, which is the product and manufacturing information that's on that CAD model. The biggest benefit here is the distinction between what is human consumable, which is that a 2D drawing is is definition that I can print out or view on a screen, but that I can look at a part, see a particular feature, and understand the tolerance requirement for that particular feature, or other specifications such as painting, welding, anodizing, and surface finish. Anything that I need to know about how to produce that part is there in that 2D drawing, but it's all me sitting and interpreting that drawing to be able to understand that information, right? I'm going to make a conscious decision if I'm going to have to quote the part to understand that information, and then to go through my manual processes and go through a team of people that will help me develop a quote that I can then pass on to the customer. Likewise, in manufacturing, if I take a look at a 2D drawing, I'm going to see, for example, a hole. It has a tolerance requirement of, let's just say, 5/10,000ths of an inch, half a thousandths. And I'm going to make a conscious decision that, look, because it's that tight tolerance, I may want to use this machine with this tooling, with this process in order to produce that hole to the tolerance that's required. Well, if I'm going to make that logical, that logical progression of steps to come to that conclusion, can I not teach digital software that strategy that it can then take if it sees a digital version of that same information? So now on model-based definition, I have a CAD model, and the nominal information is encoded in the geometry, of course, but then you also have the feature control frames, which tell you more information, the requirements within which that feature has to be produced, right? In a digital form. It's not just human consumable, but now softwares can actually read that information off the model because it's parameterized, or we call it semantic. It's semantic. And software systems can read that information in, go through that logic structure that you yourself would set up to automatically come to the conclusions that you otherwise would have taken manually, right? PMI has been around for a long time. What is model-based definition? To me, right, for the supply base, model-based definition is the consumption of PMI to automate processes. Okay, on the design side, you've had design engineers have the ability to put on 3D annotations more than 10 years, right? But for you as a supplier, on your side, when you're actually looking at producing the part, the biggest benefit to you is, again, using that data to automate processes. And as I said, I'm going to touch upon some of the technologies that help you do that, and then our technology partners are going to go a little bit more deeper into that to show you how that's done. So let's talk about the digital thread. I did talk, about the MBD file itself. You can see there up on the screen. We start at the top left at the OEM. and what the OEM supplies is requirements, product design in the form of perhaps a CAD model, but most likely a drawing, and then your PMI, product and manufacturing information. That is all of, again, the tolerance within which each feature has to be created, and all the other specifications attached to that particular design. And that gets packaged up into what's called a technical data package, okay? And once the OEM releases that technical data package to the supply base for quoting, what we are aiming to help set up is your ability to take that data in directly into some kind of a data management system, such as EPDM from SolidWorks, or Team Center from Siemens NX, or there are many other systems out there. And in a simple sense, you can think of this system as kind of, if Microsoft Teams, where if you have a Word document, it's housed in Microsoft Teams, and you can have multiple people access that file. You can make changes to that file, and other coworkers can see those changes in real time. You have revision control. There's a lot of benefit of having that Teams environment as a collaborative, platform that many people can log into and access the same file at the same time, and everybody's aware of what's happening to that file in real time. That's in essence what a data management system does for you. Is once you ingest or you take in that technical data package into your data management system, now you can reuse that technical data package across the different disciplines within your manufacturing company. So, for example, if you do any kind of analysis on the part, the analysis engineers can take that technical data package, import the model-based definition, do what they need to do on the analysis side, and then upload either the results or any modifications they made to the file or processes back into the to the PDM system, right? And now that data that's been added to that technical data package is now available for the costing, manufacturing, engineering, production, quality control. So as I said, we're going to be concentrating today on a couple of key aspects. But before I get into which ones we're going to be concentrating on, let's take a step back and take a look at the reality of digital thread and model-based definition, and really the benefit that it provides to you. So I'm gonna take the example of a particular company, right, that exists. You may or may not have heard of a company called Protolabs or Xometry. Protolabs is, I use them as an example because I tried them. And I wanted to see how a digital process actually benefits me as a customer. And so what I did was I had a need to have a part produced. It was a part that fit within a 5-inch cube. My tolerance requirement wasn't anything greater than plus or minus 3/1000 of an inch. Okay, that was about my tightest tolerance. And it was a fairly prismatic part, pretty much a squarish looking part with a bunch of features on it. Some tap holes and other features. And the process is what you see there on the screen. My first step in order to, to receive a part was to upload the CAD model. And I can upload it in several different formats. Now, at the time, I didn't upload a model-based definition file. However, I uploaded a CAD model, which for me held the intent of, all the design aspect of what I wanted that part to be. So I didn't have a separate drawing that specified anything extra in terms of the nominal dimensions of the part that I wanted. But what I did after I uploaded the CAD model was almost immediately I was presented with a screen to choose different specifications for different features of the part. So for example, I had a number of holes that needed tapping, and on the 3D CAD model that I uploaded, and in this case, I uploaded it as actually as a SolidWorks native file, again, without the PMI, but I was able to specify in the online interface that this particular hole needed a tap of 1/4" 20. This particular hole needed a tap of, a different size, and so on and so forth. And I can also specify that I wanted to have a deburring operation happening, that I wanted to have a bead blast, and then I wanted to have it, hard black anodized. So for me, that was all that's all that I required for the part, and process, that first process allows me to input all of that information. And now for process 2, obviously I can choose, like, how do I want it manufactured? And in my case, I wanted it manufactured out of CNC machining. And then once you do that, the software kind of goes through this analysis step. And then once it does that, it does it very quickly within minutes, and it presents me with a cost. And right away, I can see what that cost of the part is, and I have an opportunity to adjust certain requirements on the part. So if I wanted to change, maybe some aspects of it, if I decided to change the color, or if I wanted to not do bead blasting, if I wanted to keep it, have a different surface finish on it, I could choose it at that time, and that price updates right there in real time. I can see how it affects the cost of the part. And then once I'm satisfied, it allows me to put in a credit card information and then choose a shipping option. So I can do 1 to 7 days, 1 to 3 days, or 3 to 5 days, or out 2 weeks, and it changes the price. And once I put in my credit card information and hit submit, within 24 hours, I had my part. So the benefit to me as a customer is I know that if I need a part in a pinch, I can very quickly go to Protolabs, upload a part, and within 24 hours, I have something in hand. Why? Because they use digital processes. They're taking the CAD model, they're automatically analyzing it, they're automatically costing it, they're automatically creating the CNC process. And if I specified any inspection, they also do that as well. They provide that service. And if you think of what the DoD is requiring now, the reason they've put model-based definition in a technical as a key component of a technical data package is so that they have a supply base that's more responsive. It's a digital format that you can consume in much the same way as I presented here with Protolabs. Turn around a quote as fast as you can, and turn around a part as fast as you can. And again, throughout this presentation, we're going to be talking about the technologies that get you there. So, as I said, there's many different components to a manufacturing company. And today, and I'm not listing them all out here, but today we're going to be focusing on costing, on manufacturing engineering, and then quality control. So this first slide is very high level, introduction to a priori. They use a digital twin. They use your CAD model to essentially automate the coding process. You're going to learn more about that today, and the specifics behind that. But they also provide insight for all involved parties to the coding process. So design engineers, procurement specialists, cost engineers, and buyers alike receive the same relevant information. Their technology can help simulate the manufacturing process. So a priori provides accurate analysis of real-world manufacturing to provide design for manufacturing insights and cost estimates. And then you can actually simulate costs using digital factories. So region-specific digital factories to simulate process costs in various different regions of the world. This is an example of using SolidWorks CAM for automating the CNC programming process. What you see on the left there is a model-based definition, so a CAD model with all the PMI embedded within the CAD model. And in the middle there are the dialogues that are available through SolidWorks CAM that allow me to teach the software, essentially set up the strategies that allow it to make the decisions that result in the automatically generated NC programs. So in this particular case, they have something called tolerance-based machining. And in the tolerance-based machining dialogue, you can set up different strategies per per tolerance range. So what that means is that, for example, if I have a tolerance range for between, let's say, 0 and 2/10,000ths of an inch, I may want to specify a strategy that says, okay, use a spot drilling operation, and then a drilling operation followed by a reaming operation, right? Or a single point boring operation. Whereas if I had a tolerance range of, let's say, 2,000ths to 5,000ths, I may be fine with just doing a spot drill with a drill operation, right? And so on and so forth for other types of features. Once I have that set up, it's literally a button click, and that model-based definition, all the information goes through the tolerance-based machining dialog in the background, and it outputs the NC program that you see on the right side there. Something that would have taken me maybe an hour or so to do, to go through each feature, click on it, pick a tool, specify the parameters for the tool path, so on and so forth. It would have taken me about an hour. In this case, once I have the strategy set up, it's a button click, I get it within minutes. This is showing PCDMIS and their ability to automatically generate a CMM program. On the left there, you see the imported QIF file, which is one of the generic model-based definition formats. QIF stands for the Quality Information Framework. In the middle there are all the dialogues that are available to you to set up what you need to set up in terms of the number of points you want in a circle, number of points flat plane, so on and so forth. And then on the right side is the generated CNC program. Oh, sorry, CMM program. With welding applications, there are software if you're doing any kind of robotic welding. Offline programming software can import model-based definition. You're going to hear actually a lot more from the Capvidia folks talk about this, probably more particularly during the lunch and learn. But there is ability to import MBD files with the welding callouts, and this can actually be used to generate welding paths in an offline programming environment. For real-time robot programming, we do have our technology partners here today, Scalable Robotics. Again, they're set up over by the additive flex cell on the Atom Lab side, and they're going to be demonstrating their solution of creating a weld path using a scanning device that's attached to the robot. It actually goes over the scene, takes a quick scan of your environment, and then they have the ability to use a device that you see there on the right with a fiducial marker on it, and you just go and click on the seam, a couple of points, how you want that robot to follow the path, and then the robot actually it generates that path, and you can just execute it. So it's very, very quick and easy way of and code-free really way of programming ABB specific robots. So as I said, we do want you to see in a little bit more in depth how these technologies can be used to automate costing, CNC programming, inspection programming. And so we do have our technology partner with us today. I'm gonna shortly invite April up to talk more in depth about their solution. And then we'll have Capvidia come up and talk about, MBD file translation, automated first article inspection report generation, and measurement harvesting. And then we'll invite Hexagon up to talk about PCDMIS software about MBD file import and automatically generating a CMM program. And then again, we're going to have the demonstration over by the additive flexo with Scalable Robotics. So at this time, I'd like to invite Steve Peck up to talk more about a priori.
There. Nice to meet you. Glad to have the opportunity to give you a little bit of view into how we leverage the digital thread to support not only costing, but also other aspects of really getting to profitable designs. And at the end of the day, we're really focused on making sure our customers are getting value out of the solution. Not an inexpensive solution by any means, but when you look at the returns that can be had from implementing such a technology, it can be pretty substantial. So we work with hundreds of manufacturers across the globe. It's really focused on profitability, right? Making sure that designs are released early on with visibility to cost and the implication of the design features and how they impact the overall product cost. Are you hitting targets? And the best time to do that is early on in the design process. Also, manufacturability. We want to make sure that parts that are being released are in fact manufacturable. They don't have issues in them that will further result in ECOs later and getting to a supplier and not being able to be built. And most recently, leveraging all the capabilities that we have of predictive manufacturing simulations and machines being used and cycle times and power consumption, along with all the pressure for sustainability, we're providing insights there. So, like I said, customers across the globe in various sectors, aerospace and defense is a big area for us, automotive, heavy industrial. Company actually got started 20 years ago. We're based out of Concord, Mass. We've over 400 employees now. And 2 decades ago, a PhD student working at the University of Illinois, working in conjunction with John Deere, was working on a project and basically product being developed and not hitting target cost. So you're missing profitability goals. So thinking about how could we leverage this 3D CAD data to provide that insight to make sure that we're releasing products at target cost. And oh, by the way, when we go to buy some of those components to build the tractor from our suppliers, we want to make sure we know what we should be paying in terms of a fair price for those and being able to support those discussions. So that's just a little background on a priori. And really, I think mimicking what Nasir was saying about the digital thread, right? We don't want it to be locked up, just in a 3D CAD model. That needs to be leveraged throughout the life cycle of the product so it can be reused and automate processing. So we do that through the use of really leveraging the digital process, the manufacturing process, and a digital factory that represents the capabilities of the factory so that we can really unlock the silos that exist between departments, get design engineers and sourcing and manufacturing engineers and the suppliers collaborating over a common definition around cost, design for manufacturability, and now CO2 as well. So it really begins with a digital factory definition. So digital factory, basically, we have 80 different regions across the globe, about a dozen locations regionally within the states here, where on a quarterly basis, we update labor rates, overhead rates, material costs, all your energy factors. And that's a starting point. Our customers will configure those to match their capabilities, the machines in their facility, for example, their purchasing power over materials. We take that digital factory definition, and now we consume the CAD models, the parts, the assemblies, all the MBD and the PMI information on that in terms of tolerances and surface finishes, and really leverage that and combine it with our ability to simulate the manufacturing process. So what is the raw stock that I'm starting with? How much material is being removed for every feature? That hole has a 5/10 tolerance on it. That's going to drive a reaming operation, for example. So with that simulation, we then can review these insights, look at it both from a cost standpoint, manufacturability standpoint, and take action. Ideally, early on in the process, when you can make changes interactively with CAD and see that impact to cost. So the idea is, and I'll show a short video here in a minute, but really being able to get to a detailed cost breakdown. So this part, what's the contribution of material, labor, overhead, capital investment? Is there tooling required? Is this an injection molded part that requires $40,000 worth of investment, or a casting, for example? And provide design guidance. So young engineers, they can make parts look pretty and design great parts, but is it manufacturable? Are there going to be some features on that part? Length to diameter ratios, long skinny end mill required to get into a corner. You might actually have to, or a sharp corner that can't be manufactured, that might have to be burnt. That kind of information. And then throughout the application, providing information on why that's a problem and how you would go about fixing it. And you start this iterative loop back to CAD to fix those issues. And then the third block that you see here, manufacturing feasibility, right? Where is the cost in the overall process coming from? All of the equipment is being selected from the digital factory, and understanding of the cycle time, the high costs, and also looking at what equipment is feasible to manufacture the product in the most economic way. A shop may not have the right equipment. So on the supplier side, looking at what sort of capacity is going to be required, how many hours on this particular machine is going to be required. Should I be quoting on this job? Am I really set up for it? And if I am, what sort of cycle time can I expect for this really early on in the process? And also CO2, right? So understanding those machines, the cycle time, the energy consumption, generating an understanding of the contribution of material and the manufacturing process. What goes into making that part? We talk about cradle to gate. So getting that part out the door, how much CO2 is consumed, which is more so in Europe right now, but all over. We're seeing suppliers having to actually provide that information. One of our big customers in the heavy industrial space, on their drawings or in their model-based definition, there's a home for CO2. So definitely an area of lots of interest. So from a use case standpoint, the technology is cool and everything, but what is the problem you're solving? So we actually really provide capabilities, for what various aspects of the process. So on the quoting side, we have manufacturers that are using the product to take in bid packages and quickly turn around bids for those. So understand the capacity requirements, how they should be priced to make sure that they are going to hit profitability goals, and turn around quotes quickly. Oftentimes, first in is who ends up getting the business. Really, the big key here is, though, in R&D and design, evaluating concepts. Should I cast this versus machine it? Is this a candidate for additive? Should it be a complex structure, metallic structure that's bolted together, or maybe an integrated composite structure, for example? Making sure that design is designing to cost targets and staying on track so products are released in hitting the targets and the profitability goals. Understanding DFM issues. And then sourcing. This is, a good portion of our customer base is on the procurement side that is using this from a negotiation standpoint and a should cost standpoint. This part here, I'm making 5,000 of them a year. What's a fair price for this? And, where should I really be looking to make this? A lot of, reshoring activities. So being able to simulate in multiple regions is an important piece of that. On the manufacturing side, we have use for understanding, does it make sense to bring in a piece of equipment, for example, or make versus buy capabilities? You may have the capabilities in-house to build something, but you may not have the capacity, and it may be justified to send it out. So it's another area. And then there's always, as much as everybody likes to get it right on the front end, there's always cost down initiatives, especially on long programs, 20-year cycles. product constantly being redesigned, looking for opportunities to continue to drive cost out. So those are really the areas that we look at in terms of the application of the technology. It's really all about, starting with leveraging that digital thread to provide that cost and manufacturability insight. And at the end of the day, we've expanded our capabilities, in particular over the past couple of years, to integrate with PLM systems so that when you check into Team Center, for example, or Windchill, a design, all this analysis is happening in the background. So all the parts are being crunched at night, and designers are now looking at automated emails where they can see the outliers, which parts are over a target cost or which ones have the biggest chance for manufacturability issues. So we have, part of the platform is an analytics platform. So target cost, right? So here's my project, here's what the target is, and here's where I stand relative to that, so that you can make sure that you're on track and then focus on the areas that are most problematic. The design outlier, right? The size of the bubble is the annual spend. Each one of those represents a part. The annual spend, it's actually a cost versus weight graph. The color of the bubble is indicating manufacturability risks. So the parts with the dark purple have the highest risk. They've got sharp corners in them, or sheet metal parts with bend radii that are too tight, that are going to ultimately result in changes coming back, or hopefully not getting to the supplier and not showing up as not being manufacturable. And then regional sourcing, looking at that, all the different places that it could be sourced from. What's the most economical decision to make there? And then this last one here on the bottom right, sourcing outlier. So loading in what you're currently paying for a part compared to what the should cost could be, so that you can look at the parts that have the biggest difference. Those are the ones that you should pick up the phone and have a discussion with your supplier. Something's wrong. Maybe they're just justified, but maybe the equipment they're using is, way more capable than necessary. So that allows that fact-based discussion. So with that said, let me just play a quick video here and give you a view of it in action. There's some voiceover, but I'll skip that. Let me see. There we go. So a priori supports all sorts of manufacturing technologies, over 450 cost models. So your sheet metal to machining to composites to additive manufacturing assemblies. It started, 20 years ago, heavy metal, sheet metal, and welding, and has grown since then. So it starts with the 3D CAD model, bringing that into a priori, specifying the high level process group. So is this a sheet metal part, machined from stock, a casting, a forging, additive, followed by the digital factory? Where am I making this in the world? Which of those 80 different regions, or a configured factory? So some of our customers they know the capabilities of their factory, the machines. The digital factories can be tailored to specifically match a supplier if you have that relationship, that you have that insight, or an internal factory with capability to really hone that factory in. And part of that is all of the materials and, of course, the cost per material, but also mechanical properties that are used in the manufacturing simulation. And all of the different grades of materials that are specific to the manufacturing process. So if I'm looking at an injection molding process, I'll see all those. All the data can be imported and exported as necessary through Excel. And then lastly, how many am I making and for how many years? So understanding the batch impact, which can have an impact on the overall cost of the parts. And then the simulation goes and does a thing after answering those few questions. And you can see here that this sheet metal part is going to a turret press and then a 3-axis mill. So we've actually analyzed all the different ways. So is this going to a laser in a bend? All the different manufacturing processes, looks at the feasibility and then the cost, and selects the most cost-effective approach. So in this case here, you can see this is a list of the machines that were cycled through in order to the turrets here and it's selected first off, is it capable? And then the most appropriate from a cost standpoint. And you can see the cost breakdown here with material, labor, overhead, all of your cost breakdown. If there was a capital investment as well in terms of tooling, that is captured with, basically within a couple minutes of, pulling the CAD model in and running it. The design guidance provides information on potential manufacturing issues. In this case here, there's an edge proximity. So I've got currently at 2 millimeters, it's suggesting that you're at least 3 millimeters from the edge. And here's why that's a problem. So that gives that insight to the young engineers that may not necessarily, have a full understanding of all the design rules. And here you can see the MBD. So tolerances were pulled in, and this machine, the turret can hold a 7.07 millimeter, but the tolerance is at 0.02. So that drove a reaming option on a 3-axis mill. So if I could loosen that, I could eliminate having to get that to the 3-axis mill, the setup, and all the cost associated with that. And all of these assumptions that are made from the cost model, sometimes you'll want to dig into the details. All the detail in this case, the overhead breakdown. So the energy cost, depreciation cost of that equipment. And if I want to go in and having a discussion with a supplier, okay, instead of $28, you're at 40, okay, I understand the reason why, and update quickly to understand that. Here's a rotomold product. So a priori is specific to the geometry in the manufacturing process that you specify. So in this case here, there's a bunch of additional options that you could set. So, and perhaps there's colorant added. That level of detail can all be accounted for, set in defaults based on, your standards. And then here, lastly, jumping into electronics. So that's a big space for us as well. PCBA and wire harness. We integrate with a system called Silicon Experts that you load in a bill of material, and this system provides feedback on minimum and average price for those components. And then we take that in, just like we did with a sheet metal part or a composite part or whatever it may be, simulate the manufacturing process on what it takes to assemble that, in addition to the cost of all the components. So you can see a breakdown here. In this case here, the assembly cost being at 27%, whereas the components are 77%. So handling not only individual parts, but components. And then it kind of wraps up with, okay, we've analyzed all these parts in the simulation. Let's now make some decisions around it. Focus in on the parts, in this case here, current cost versus quoted cost to know which ones you're overpaying for, or here an analysis of China versus Mexico on a variety of parts. Does it make sense to reshore? In this case here, a machine capacity requirement on a part. How many hours am I going to need on the 5-axis so that I can, if I'm quoting it, or if I have a transparent relationship with my supplier, I can provide those insights. So quick overview, but the idea is really to leverage the model-based definition and the digital thread to provide cost and manufacturability feedback early on in the process for a variety of use cases. Thanks.
Thank you. I really much appreciate that, Steve. I'd like at this point to invite Daniel Campbell up from Capvidia to give us his presentation.
All right, thank you, Nasir. Yeah, well, thanks everybody. It's great to be back here at CCAT again. For everybody attending online, if you haven't been into CCAT, I'd really encourage you to come in. It's a great facility here, excellent technology, and they have a great team that really understands the technology, how to integrate it, how to get value from it. So come on in and visit. So a little bit about Capvidia. So we're a provider of model-based definition technology software. Model-based definition, I mean, today we're going to be focusing a lot on naval maritime applications, but really it's a technology that's applicable, and it's a really growing technology in all different areas of discrete manufacturing. So we deal with, all different kinds of industries. What we try to focus on with our approach to model-based definition is how our customers can immediately start to drive some value from their model-based definition implementation, because it's a process change, going from a 2D world into using 3D and using 3D annotations. And so the question is how can our users immediately start to drive some value from this instead of it just being purely a cost sink? And a couple of the areas that we've really seen most of the value coming out is on the quality side. I mean, this is really, especially at first, where you can start to drive value. Earlier Nasir was showing some slides that show, simulation. You could derive a lot of benefits in terms of model-based definition in that area. Into costing, we saw an application with a priori and how MBD can drive in that area. Into manufacturing, planning, production, quality. But it's especially today, we're going to start on a real high-level workflow that Rudy's going to show, which is usually kind of a first step of how you could start to use model-based definition and derive some value for your organization. Just a quick background on Capvidia, on our products. So we'll be focusing today on our MBD-Vidia technology. We also have our Capvidia technology, which is a comparative validation and a CAD checking tool. Basically, the idea being that if you want to use the model as your single source of truth, you want to make sure that it's a high quality model since you're basing so many processes off it. So that's what Capvidia is focused on. But today, again, we'll be talking mostly about our MBD-Vidia technology. And a little bit of what, an important aspect of model-based definition is standards. And so something that you'll hear a little bit about today is the QIF standard, which is an ISO standard that helps to tie the design world, so your CAD and your PLM product definition data, to your quality data, which is your as-built data. So, at the end of the day, what this helps with is you have your as-designed model, you have your as-built data, and this is how you unify these things. So you hear people talking about digital twin. This is one of those ISO standards that's out there that really helps you realize that. And with that, I'd like to just pass it along to Rudy, and he can kind of walk us through this workflow.
Thank you, Daniel. All right, guys, we'll spend a little bit of time going through the workflow here that Daniel was talking about. I have a quick video. I'll just browse through this chart real quick. So we're going from the CAD all the way down to CMM inspection. That's where the guys from Hexagon will be taking the presentation, showing you what and how the inspection will go and sourcing that MBD data. So let me go to the next slide here. Perfect. Okay. So we'll start at the CAD level. In this case, we'll be showing NX, but this can be done in any CAD. It could be SolidWorks, it could be Creo, CATIA. We're bringing in a CAD, and once again, it's MBD, right? It's all defined in the 3D space. This case, just to highlight, we do have welds, just specific for this model, just a weldment. You saw the demo done by the guys at Hexagon over here. That's the part that we're showing here, right? Importantly, we're going to be exporting this file as a QIF standard. That was what Daniel was talking about. This is a standard that brings in the CAD and also the PMI. So all the GD&T will be all put in one single file. After that, we're going to be bringing that over to MBD-Vidia, which is our core software. You can see here, we're just having the same exact CAD geometry and the views and all the GD&T that you saw at the CAD level, in this case, NX. All the views are shown there. Now to highlight is that after that's been done, we went ahead and characterized each one of these items. So now each one of those GD&T callouts has a designation, a character number. Very important to show, and I'll show it again in the next couple of views, is that each one of those holes that you saw, there's 12 holes, has a sub-character number. So it's going to be traceable throughout the workflow. Very good. Hello, yep, there we go. After going through this, we're going to be exporting this into Excel. This creates an inspection plan. So if you guys have worked in quality, you've seen these extensive inspection plans where it includes all the dimensions. the results and everything. It could be an ACE 9102 report or just a standard format that you may have at your company. But what our software does, it actually exports that automatically into any format. Also, what we're showing here is this is exporting the data over to NetInspect. For those of you that are not familiar with NetInspect, NetInspect is a cloud-based QMS solution, and it pretty much automatically pushes all that data, all the GD&T, no manual input, up to NetInspect. This is very useful for your supplier base. If you have suppliers that they can submit their first article inspections to NetInspect, and you can approve directly from there. So we work together with them, and we have a very good relationship to manage all this data. So at this point, we'll bring him back into Capvidia. Really, the process could go either way. But here we want to show how we are segregating the wells as a different tab inside Capvidia, meaning that we can really show how these wells could be managed as a separate inspection point, separate inspection plan. So potentially at your facility, you have a different group manufacturing wells and inspecting wells. So that's why we show it as a little bit as a separate segment. It could be combined if you wanted to, but it just gives you the ability to really manage your inspection plans as you want it to. Right, so we'll just showing a quick view of how the Excel sheet has the data and it shows the views, making it very easy for an inspector to really review the information. From here, once again, showing the wells there too as well. And from here, we should be moving along to the other way of showing the data for the inspectors, suppliers, which is our lightweight view. Well, it's a 3D HTML. So from Capvidia, you can export this 3D HTML. And this file can be used to visualize your 3D MBD, your model, your bill of characteristics, which is the kind of like the list of features that describe the model. You can see here, you can rotate it. This can be open in any browser, so you don't have to download any software or anything like that. And you can really visualize all the GD&T and how that's referenced on the actual feature, on the actual model. So once again, to highlight, right here, the software went ahead and characterized each one of these holes individually. So if you think about it, throughout the workflow, that hole, 8.1 hole, that hole on the left top-hand side, that'll stay the same reference. So you have 10 serial numbers, they're all going to be compared to that same reference. So you're always keeping the same reference feature. And after that, we would pretty much push this over to CMM. This could be, for example, we're using PCDMS at this point, and that data, that QIF file that was generated from CAD can be directly imported in PCDMS with minimal manual programs. So we'll take it over to the PCDMS folks, and they can actually show a quick workflow of what happens there. Then we'll bring it back to us and show you a little bit about data harvesting.
Hello, everybody. My name is Sean Grady. I'm a local sales engineer here for Hexagon Metrology covering Western New England. So I'm going to be going through the slides here, talking about, give everybody a brief overview on Hexagon, and then more of the technical side as to how to import that model-based definition into PCDMS and go through the necessary steps. For those of you who aren't familiar with Hexagon, today, again, we're talking about the quality aspect of Hexagon, but we're also into design and engineering software as well as production software. And we've been making great strides over the past couple of years to try to get all of these three divisions to talk to one another. So as we start measuring something on a CMM, if there's any offsets that need to be sent back to a CNC machine, we can handle that, as well as send some feedback back to the design engineers and help close the feedback loop for our customers. A little bit more of a background on the design and engineering. Here we get into helping design structures, acoustics, some virtual manufacturing, materials, system dynamics, as well as some autonomous, simulation, physics, and applied solutions. On the production side, we have software that helps do the machining, mold and die design, sheet metal fabrications, woodworking, simulations for the CNC machines, as well as in-process inspection. So we have sensors that can go inside the CNC machines to help inspect at the CNC and gather information. And then most of you are probably familiar with Hexagon from the metrology slash quality side with the CMMs, with a wide range of different machines, such as the standard bridge CMMs, the arms that we saw earlier today, as well as some CT machines, automated inspections, structured light scanners, and other things. Another little background on Hexagon is we're a very global company. Here you can see the breakdown of where we are positioned across the world. We have over 8,000 employees. We take 10% of our net sales, put that back into R&D every year. You have more than 500,000 software licenses installed, and we have up to 2,800 different software developers and engineers to help always add new tools to our portfolio. So today what we've been talking about is the model-based definition. So here's an example of how our current workflow is in a brief snapshot to deal with the PMI. But in a lot of cases, for people out there who are familiar with CMMs, typically you might be dealing with having a part, a drawing, and a CAD file. And like we've discussed earlier, is that somebody would be basically interpreting that drawing, deciding how to measure the features, typing in information for your tolerances, and anytime there's an operator involved, there's human error. I'm a former application engineer, so I can say myself that I have fat-fingered the keys at times. But this is where the whole model-based definition comes into play to help eliminate that stuff, as well as to create a program fairly quickly, for your inspection process. So we typically start by importing a file. PCDMS has some tools to generate the GD&T. We then, have certain methods and strategies to measure certain types of features, depending on whether it's a circle versus a cylinder or a plane. PCDMS will then execute and capture the results, and then we can output the data into a few different formats. So on this particular slide here, what we're seeing is the importing of a QAF file, UG file, CATIA, ProE, SolidWorks, any native format that has the embedded GD&T within it. Here we're bringing in a particular file, and as soon as we do, it automatically recognizes there's n number of entities within that file, and you have the ability of having it to simply accept that information and create all those dimensions and features for you. So in this particular case, we see that a program has been generated, and we now would have the ability to run this particular program. Now, in some cases, we don't necessarily want to do exactly that because we might be aligning something a little bit differently one way versus another, going off of a fixture or something along those lines. And that's kind of where the next step or the next file comes into play here, where once we import the model, traditionally what we end up doing is looking at the geometry in maybe the different views that we have to work with. And by using a shift key plus the left mouse key, we can hover, and you can see the little animation, the video over on the right, the necessary dimension that we're interested in. And simply by clicking on that, it's going to bring up a tool and or a dialog box to enter not only the feature, but also that dimension with the associated tolerances into the PCMS part program. And that's what we're seeing here at the moment. So in this case, it's a circularity that they're working on. And then there's also a perpendicularity that they have here. So how do we handle the different types of geometry? Well, like Nasir had mentioned earlier in part of his presentation, is certain softwares use certain measurement strategies, and that's how PCDMS handles things. So what the user can do is they can define, okay, if I'm going to be measuring a cylinder, I want to measure it a certain way for most of the time. And so you can define whether you want to probe it, whether you want to scan it, how many points you want on it, how many levels, those sort of things. And so basically you're defining all this stuff up front. So now as you go and click on the geometry, like we can see here in the particular views, we can just simply hover over the feature, and PCDMS recognizes whether it's a plane or a circle. In this case, it's going to see a couple cylinders here. And by left mouse clicking on it, it's now going to add those necessary parameters. In this case, it's a cylinder taking n number of touch points at 3 different levels into the program. But with our systems, we have many different sensors and configuration. So we can, depending on what you're using for the CMM, you can take individual points, you can do some drag scanning, you can do a bunch of different things. And that's, again, what we're defining here. So what'll come up in just a second here is if we want to measure some circles, we can click on those individual bits of geometry, or what we can do is utilize this CAD file and just simply highlight a plane that these features are all embedded in, and then it'll recognize all the necessary circles and write the program for us. And that's, again, what we're seeing over on the left-hand side, you know, with this particular view. So just bear with me for a second as the software goes through, though the video goes through. We can see in just a minute. Here we go. So now what it's doing is actually executing that routine. And we can see in this particular case, it's drag scanning for that particular circle, as well as the other ones over here. So it's using those measurement strategies to basically go through and capture all that information. Now, you always have the ability to go and edit things, you know, if your strategy isn't necessarily going to work with this particular feature, but it works for 90% of them. You have some quick and easy tools in order to do that. And you'll see that in a video that I have at the end. Once everything is captured, we have the ability to send it out to a number of different formats. In this particular case, we have a standard piece of EMIS report. We have the net inspect that, you know, we were talking about just a few minutes ago. And then we also have our own Nexus metrology reporting, which is like a one-stop hub in order for other people to take a look at all the data. And we have a couple little videos here. So this one over on the left-hand side, you can see our standard piece of EMIS report. We got a CAD view here that we can, you know, interact with, that we can orientate the view for what's being shown for the dimensions that you see on that particular page. And then over on the right-hand side, you know, we have another little video that's just starting now where we can see multiple different parts. So this is more like a hub or like a web browser type thing where you can take a look at individual parts. You can dig a little bit deeper on a particular part where you can now look at a bunch of different dimensions. You can do some filtering for, you know, critical dimensions, out of tolerance dimensions, and you can gather more information in one particular spot. This last one here is we're showing that example for the Excel template from Capvidia. In this particular case, what we're doing is some customers might want to run an existing program and after each one, create one particular report for that part. Other customers might want to have a run where multiple part runs are all embedded in one particular file. And that's what we're doing here. So you can see we have part number 1, part number 2, part number 3, all embedded in this one particular file. And this is what will eventually, you know, in a few minutes get sent back to Rudy to show the tail end after we've captured the information from PCDMIS. Now, this video here is a start at the beginning of how does this work within the software. So basically, we did a file new. First thing that comes up is our probe information that we're seeing here. So I'm turning off some of the graphics for the probe just to make it a little easier for us to see when we import that QIF file. So once we bring this in, we can see it has so many entities, but I simply turn that off so we can look at the different views, because sometimes there might be a lot of stuff on this particular file. So we have a top view, a side view, a front view in order to interact with it. We also can set up what we refer to as a clearance cube. So this is basically going to be a safe zone or position around the extremes of the parts that we can resize, that I don't have to worry about movement with my probe. Now, all I have to do is click on the dimensions. It's going to add them into the particular program. And now the machine is going to be handling all that particular aspect of it. So what I ended up doing here was I clicked on Datum C, and I didn't want to use one of those direct strategies because the part has a lot of obstructions here. So I'm actually choosing the particular path in this particular case just to show some flexibility on that particular plane. Now, when I go and click on that other dimension, the same sort of thing. In this particular plane, I simply want to go down and I'm going to take individual points, and this is where the machine is going to go. So I'm basically just setting up a path to avoid the different bits of geometry. At that stage, I can just simply click on some features and in this case, use the strategy. I don't have to do anything else because it's a very simple measurement that I have full access to. Now, in this particular case, I'm changing my probe to orientate. So I'm now going to be able to measure stuff on the front face. And so I'm just changing the view. I'm going to capture these distances. And again, these are certain planes that are not well-defined geometry. A plane infinitely can go on forever. So I want to take specific points, especially on this little tiny step here. So I'm just going to accept that there. And then when I go to measure this other plane that was part of that distance dimension, I'm again going to choose my individual points. After we have this, we're going to change the view so we can then see some of the different datum features, such as the 12 holes that make up that pattern, and one of them is datum B. So by clicking on that, it's going to add all 12 holes into the program. I'm going to be stepping through just so you can graphically see it go around and show you where all the information is on these particular features. And I can see right here from my background, in programming PCDMS, is that it looks to me that these circles might have all been created all in one direction, sort of just punched through the particular part. So I'm going to do a little bit of editing here. So PCDMS has a lot of flexibility to quickly edit things. So basically what I'm doing is I'm just simply flipping the vector from one direction. I'm going to grab it directly off the CAD file to becoming out of the part coming towards us, because that's where our probe is going to be sitting. So I'm just going to edit those 5 or so holes. And then we can move on with the program where we now are going to capture the 2x diameters over on, actually holes on the backside first. Nope, that one there. So I'm going to be grabbing that one and then the one on the backside. So again, the same sort of thing. If this hole was punched all on one side, we're simply going to flip it so it's coming from the opposite end of the part. And I'm adding one dimension here so it shows up on the report. And then what I can do is rotate this probe back down to capture the last couple of dimensions, which are going to be these particular profiles with our 60 thousandths tolerance, one just to C, one to A, B, and C. So we got this one here, just accept it, and then that one there. So what the model-based definition is doing for us is that this process would take quite a bit of time, to add everything, make sure that you got all your nominals, your movement and everything created. But you see here, now we have a program written where we have the tolerances and nominals directly coming from the QIF information with that embedded GD&T. And at this stage, it's a matter of, all right, let me close that. I'm going to zoom out a little bit and I'm going to reactivate all my probe components so I can see not just the stylus, but the probe sensor, the wrist, and now I could run an animation and look at any sort of collision detection. So in this case, we're just simply running the program. And as you can see, it's going to that safe zone. It's now following the path that I had created with those individual points for these 2 planes. Here's the plane on one side. There's my probe rotation. So you can see it will come up and over the part. I don't have to put any of this movement into the program. Going to take the individual points. Now it's going to measure the cylinders on one side. It will then come up and over, rotate, go to the other side, come back down. And then at that point, we would have a report with some measured data, which then we can pass back to Capvidia for the net inspect. So as you can see, we programmed this part in just a couple of minutes. And at that stage, again, a report was created and we will be passing it back to Rudy.
Thank you, Sean. How are you doing on time? All right, guys. So very quickly, just wanted to summarize this workflow. We went directly from CAD, full MBD definition, all the way through creating your inspection plan, creating a lightweight viewable that could be used at the supplier base at your shop, going all the way to actual inspection, minimal touching of the programming. So everything is done very quickly. And that's, I think, the key point to take here is that there's minimal intervention from an operator like it used to be, where you had the drawing, type in your dimensions, program your probe, etc. So you're really minimizing the amount of work you're doing. Let's see, the next one is a quick video on harvesting the data. And what that means is we're grabbing the data that's been inspected, and that data is going to be brought into Capvidia. We'll show in a little bit. And it could be used to compare, to analyze, to make decisions. And this could be pushed all the way up to engineering, where the engineers can actually see what having this data means, right? Oh, should we change our design? Should we open up the tolerances? The intention here is to make this closed loop where engineers can actually see the data and say, oh, wow, this is what the actual part is. Because a lot of times inspection data just ends up in a hole and nobody knows about it, right? So we want to bring and close that loop up and have engineers see it. Once again, that data was brought in, can be brought in from PCDMAS, from NetInspect as well. And you can see here, there's several serial numbers shown. And as you click through each one of these items, each one of these holes, you're going to see different ways of displaying the data, which makes it very easy for somebody to make a decision as to what they should do. Should we change the type of operation that we did for the CNC because we're not meeting the tolerances? Should we look into different approaches? So the intention here, once again, is to be able to make a decision at the end of the day. Once again, we're showing just different ways of displaying the data. You can also do statistical analysis if you want to, but once again, we're grabbing this data so you can make a decision. So really, that's it for us on the harvesting of the data. I think, Nasir, you can take it over now.
Thank you. So at this point, well, first of all, I'd like to thank all of our technology partners for coming and giving us a deep dive about the capabilities of their software. I hope you saw how digital file can be used to help streamline processes. Again, there's many different components to manufacturing, supply-based, business, and we talked today about streamlining costing, streamlining manufacturing, particularly CNC, using model-based definition, and then also inspection. If you can do those three things, you focus on those three things first when you're in your journey to adopting, digital thread technologies, being able to use model-based definition, that gets you 80% of the way there. So if you're looking at, what do I do for my business? I hope that those three items you saw today are what we feel, at least at CCAT, what we've experienced with helping the supply base. Those are the three categories that help the most, and what we would recommend you focus on first. So at this time, I'd like to invite Daniel, I'd like to invite Sean, Rudy, and Mike up for a question and answer session. There's microphones there in front of you. If you want to turn those on and ask your questions, this would be a great time. And anyone online, if you could, again, use the question section of the Zoom meeting, or the chat section, I'm sorry, and just post your questions there, and we'll have them read out loud here, and we'll attempt to answer your questions. Okay. I'm sorry, Steve, I didn't mention you. Thanks for coming up as well. A quick note about the mics. We do have an active noise cancellation on the mic, so if you end up holding it kind of further away, it picks it up as noise and it just mutes you. So just keep it close to your.
That's the problem.
So forgive me for my rudimentary question here, but through this whole MBD process, what configuration, has configuration management been taken into account? Say down the road, after you upload your MBD file and down the manufacturing process, something needed to be changed to that original design. So what configuration management features or, I guess features have been incorporated as part of this process?
Yeah, thank you. That's a great, and it's a really important question when it comes to MBD. The answer is that, yeah, configuration management is a big deal. How MBD is managed, I mean, it needs to be managed within the context of PLM. And I mean, I think overall the answer is that things are managed in a better way, in a more formal way. You know, the way that things maybe often can be managed right now is very ad hoc. Even you might have certain documents being managed and configuration controlled, but at the end of the day, it's often they're human readable documents, maybe PDFs and things like that. With model-based definition, you could start to take very specific CAD information and keep that configuration managed so that you can go through processes where you have a part that works through multiple different revisions, and you might change your CAM program for that. You might change your CMM program as it sort of marches through each of the different revisions, and you can keep so you can sort of track what's changed between each of those different revisions to do, for example, a minimal update to your CMM program from one revision to a next. And so there's a lot of intelligence that can be added to your process in terms of configuration management. Yeah.
In terms of lowest hanging fruit, you know, where for the average company that's, for example, saying utilizing mostly manual processes, or they've got a standalone CNC or a CMM process, which of these products, and obviously this is going to be a different answer company to company and application to application, but what's the lowest hanging fruit, earliest first bites? I mean, obviously coming up here and talking to you all at CCAT and talking to each of you guys as solution providers, but where is the easiest point of entry for your average company that you all interact with to start exploring the most appropriate place for them to onboard one or a combination of these products and processes that's going to be able to show them either you know, early efficiencies in terms of streamlining their own processes, or automation, or in terms of better interaction with either their suppliers or their customers? And I know that's a broad question, but yeah, I'm sure each of you guys see where, you know, compared to say a John Deere, compared to a Boeing, for the average small to medium manufacturer, where do you see the easiest point of entry and the you know, the earliest point at which they can start that trajectory towards a more digital factory or digital automated processes?
I'll start by kind of giving my experience with working with the supply base. I often see there are technologies that companies onboard to help in manufacturing and production, but it's typically in the metrology area where companies tend to lack. They tend to do hand layups and even you know, not wanting to let go of the tried and true kind of familiar ways of measuring things, where you're either doing it manually or you're doing it on systems that are somewhat old, but they're just the way in which you have done them, and it's something of a skill level that has been developed over time, where you know you have this expertise and you're kind of hesitant to change it. I see that more where if we walk into a company, there's typically a bottleneck at metrology. I mean, companies can sometimes produce parts faster than they can actually measure them. And the reason I even pick on metrology, not only from that standpoint, but if you look at, for example, Hexagon talked about, you know, non-contact inspection, like laser scanning. That has always relied on a model. If you want to do a deviation map, you know, you bring in a model, you take your scan, you do a deviation map, and it's inherently model based. And you have the QIF file. That's a very mature file format, even more so than the Step 242, if I'm not mistaken. And that's been around for quite some time. So it's on the metrology side, if you adopt, for example, PCDMIS, if you're using a CMM, right, and maybe you just need to onboard a module, like for example, the CAD translator or the QIF importer, right? That gets you a long way. It's a small investment, and it gets you a long way in the process that to change the current process that you're using. So from my standpoint, I see metrology as being a very easy way to implement model-based definition and to at least streamline that process, because typically, as I said, we do see companies bottlenecking in metrology. So
Just a little add on that is that I agree with Nasir 100%, because what we see a lot of times is that metrology is the bottleneck. Like you said, people are manufacturing parts much faster than they can inspect them. So if you have to write that first piece program, by having the model-based definition, you saw with my slides that you can do it very quickly. But the other benefit is that there's still a lot of people out there that don't truly understand GD&T and don't really know the meaning of that feature control frame, whether it's an ABD alignment or ADB. Those are two completely different things. Well, the model-based definition takes care of that for you. So by clicking on that dimension, they don't necessarily have to be truly skilled on that. Obviously, it's nice to know that in case they need to make some necessary changes, but the software is going to be basically writing the program for you in that particular aspect.
And one thing else to add, and I think the bottleneck, we all see it is a lot of times in metrology. I think we could also look into, not everything has to go to the CMM, right? And if we can define an inspection plan ahead of time that tells you, you know what, we only need 10% CMM or we need 50% CMM. Everything else could be done at the in-process inspection with a caliper, with an arm. So if we can guide the inspection to just be the critical items, then you can really make it efficient, right? And you can really, like you said, really, that's, I think, a key part of it is finding the low-hanging fruit is really using your tools as best as you can, using the CMM when you can, using manual options when you can, and just being able to manage that. I think that's good.
A quick step from the costing standpoint here, I think we're up against it. If I look at the suppliers, estimators, bottlenecks, spreadsheets are the biggest competitors that our company faces, right? People that just aren't leveraging that 3D, doing things in bulk and being able to take advantage of that digital model that's out there. And they're relying on experts and manual tools. We look at it on a lot of the companies that we work with are the bigger OEMs out there and tier one suppliers. They might have cost engineering teams of 300 people that are doing this, homegrown spreadsheets that go back decades. So that's just, the eyes are opening in terms of how you really can leverage that. And the quick wins for us, we do a value assessment workshop, and usually the OEMs, it's on the procurement side, give us 50 parts, give us what you're paying for them today. They often push back because they want to test you on results, but it's like, all right, gave us 50 parts. Here's 5 that the software within, 20 minutes bubbled up as being differences here. And it's just relying on the automation and that ability to leverage the 3D model. And I think it's just continued education. I've been in the model-based definition world for 20 years here on programs, and we're seeing an adoption, start to pick up.
Thank you very much. And just a follow-on question, I think on both the on what I'd call the intake side and the outgoing side, so you've got your quoting on the intake side and you've got your inspection and first articles on the outgoing side. Do you guys in your various sectors and areas of specialties, do you see a lot of uptake and willingness from the OEMs or the first tier that are eagerly, I mean, if they're not, I guess it depends on the OEM or the first tier that you're referring to, but what's the willingness and the compatibility on the OEM side or the first tier side to really utilize this, and how does this play into performance indicators and performance metrics from the OEM as it pertains to a supplier? Is that something that most OEMs, I know, I think I would say that in the submarine industrial base, we're probably a little bit slower than say aerospace or automotive. But, you know, we're starting to see that really favorable tendency from an OEM looking down towards suppliers that are beginning to onboard these technologies. Are you guys seeing any of that in your applications?
I'll take just a quick stab at that. And one of our best examples in the most advanced, customer OEM supplier relationship we have was with Alstom Trains. And they have about 15 dedicated suppliers that they've gone through and validated the results coming out of our solution on the 3D tools. And they've been very transparent. They've actually agreed on the results, and all they have to agree upon, they set a margin and they send orders to them and they take the orders. Not everybody is that transparent, but that's a great example. They call it zero RFQ, and there's some suppliers in that.
Yeah, I mean, some thoughts on that. I think just building on that, I think the key is to have a very interactive relationship between the OEM and its supply base. It is, in our experience, it is usually the OEMs that are pushing MBD. I mean, it's sort of, they're the owners of the design typically, and so they'll sort of push that downstream. So it is the OEM's responsibility. But we've seen a lot of cases where the OEM will generate some poor quality model-based definition data and just kind of kick it downstream and say, good luck. And I mean, what you're doing there is you're setting up your suppliers in a situation to fail. They're starting with a position of bad data. They haven't been given maybe, the proper training in terms of how to make use of the model-based definition data and things like that. So what we've seen in terms of what's a very successful approach from, an OEM to a supplier relationship is, first of all, that the quality of the data starting from the OEM has to be high quality. And then secondly, when that data is handed down to the supplier, that there should be a very interactive relationship like that. First of all, the OEM should work actively with the supplier to talk about how they're going to use that data, maybe encourage the suppliers to get involved at organizations like CCAT and the Naval Maritime Consortium to understand, what are some of the best practices out there in terms of using this type of technology. And when a situation like that takes place, then you really do start to see, some of these suppliers like really being able to add value, maybe make parts at a higher quality or faster or cheaper because of model-based definition. And so you start to see sort of a payoff all around.
Fantastic. Thanks, Dana.
Yeah, I'll kind of add something to that. As Jackie mentioned at the beginning, we do have, federal programs. And one of the federal programs that ended, I think it was July, August time last year, we're just waiting for the second phase of that this year. And it's all about, digital model initiative. It's about helping the supply base adopt, digital technologies to essentially automate processes, as we've talked about here in today's presentation. And this federal program is an indication of where, the federal government is putting money into these types of programs that help with the adoption of the technology. But it also, in this particular, here in Connecticut, what we're doing is we're working with the OEMs and the supply base, because as Daniel mentioned, the supply base doesn't always get the best MBD model. So as an example, I'll take SolidWorks because I tend to see it, a lot of companies using SolidWorks. In SolidWorks, if you create, let's say, multiple holes in a part, it can be a pattern feature, right? Or in any CAD, you can have a pattern feature. And if you have the MBD module for your particular CAD, you can go in there and click on one of the holes, and then you get a little dialogue that comes up, or depending on what CAD system you're using, you have some option to specify how you want to put the PMI on that particular. Do you want to specify just that particular hole, right? Do you want to specify it for the pattern feature, right? In another example, you have, let's say, a counterbore hole that has, in essence, 4 measurements. You have the diameter of the counterbore, you have the depth of it, you have the diameter of the hole, and the depth of the hole if it's a blind hole, right? Or in this case, it would be a through hole. But in one in one click of that particular feature, if you created it using a counterbore feature within the CAD, right? You pick a point and then you specify the counterbore, specifications in a dialogue. In CAD, that's a counterbore feature. It's not, two different holes. And so when you put the MBD feature control frame on there, it gives you four or three different measurements in that one feature control frame that when you pass that down, so on the design side, that's great, that's fantastic. But what about you as a supplier? When you receive that data, how does your inspection software interpret that? How do you interpret a pattern feature, or how do you interpret a feature control frame that has multiple different measurements in it? So where this particular program is all about giving that information, understanding from the supply base what you're receiving, seeing the difficulties that you're having with automating your processes using that model-based definition, and then providing the feedback back to the OEMs. In this particular case, we're working with Electric Boat, Pratt & Whitney, Sikorsky, and Collins Aerospace in this next phase, to inform them of this. Hey, it's great that you're putting it on that way from the design perspective, but when you come to producing that part, you got to split this stuff up, because you're going to have a different identifier for each one of those measurements in that feature control frame. So, like I said, if the federal government is putting money into this, and this is a long, even the state of Connecticut is putting money towards this, it's up and coming. Like I said, there's a standard around it from the DoD, and this is the kind of technical data packages that they're going to be outputting. And the expectation is that when you receive that, the supplier doesn't split it in the sense that when you import that MBD file, you don't create your 2D drawings and then go about your typical processes. In the journey to adoption, yes, you're going to do that up front, to be able to accept the file and continue with your general processes. But the hope is that eventually the foresight is that you want to use this data to automate those processes. That's the whole point, to streamline all of this. So I hope that in part answers some of that. Yeah.
So from the non-engineer in the room, from a workforce development point of view, what kind of uptraining are you going to have to do with your staff to get them from, all those spreadsheets and whatever to where you are?
I guess I'll start. Yes, sometimes when you adopt model-based definition technologies, it can be as simple as an add-on to an existing piece of technology you have. For example, I'll give the example of SolidWorks again. I can purchase the MBD module. I could activate certain features in the CAM solution of SolidWorks that enables me to do certain things. So in that particular case, where you have an environment, right, that you're used to, it's easier to upskill the people to use this added capability that you're turning on in the software that you're familiar with. Okay. It's the mindset of going from a traditionally manual process and from using the years of experience that a person or a group of people or a team of people have to accomplish a certain task, to embed that information into a piece of software so that it can then do it itself. Now that's a culture change, right? That's something that takes a little bit of time to settle in. There's some resistance to that sometimes. Software's not going to do it better than me, right? But the point is that the software is there as an aid. It's there to streamline things that you don't necessarily need to do manually. But from more specifically on the training side, if you're adopting technology that you don't have in-house, it's a completely new, piece of software that you're going to be using. Like for example, as Stephen mentioned, if you're going from legacy, Excel spreadsheets to a priori system, that's a significant amount of training that's needed to upskill the workforce. Now, I can tell you that at least from the CCAT perspective, the state puts in a lot of money to help fund, the supply base training programs. So we do have a collection of videos on our website that you can access that go through step by step. They're on-demand videos that the supply base can use to get familiar with the technology, to get a little bit more in. There's motivational videos, but then there's also, like I said, very, very in-depth step by step. We do hold technology trainings here at CCAT with our technology partners. We'll invite them in. We'll set up our training rooms. There'll be a day to a week-long training programs. Again, a lot of this is paid for by the state. There's minimal to no cost to the supply base out there. So there's quite a lot of funding being put into not only the adoption of the technology to help you pay for the technology, but then also to upskill your workforce. And we're going to talk about, Eileen particularly will come up and actually talk about some of those grant opportunities available to you to help alleviate some of that cost that a company has to take. So thank you again to our technology partners up here. Really appreciate you taking the time out to come here and actually help to have companies understand what these technologies can do. So really appreciate your time here. Sure. So some of the programs that we have available, through CCAT, again, funded either by the state or federal government. We're just closing out on our Industry 4.0 program. It is still currently active. And in this particular program, what we do is we start with introductory workshops so that companies get an understanding of the types of technologies that exist. This is kind of getting to know what you don't know. And then we follow that up with technology demonstration projects. So if you have particular challenges at your companies, please invite us. We'd love to take a tour of your facility, understand your pain points, and then we can bring those back and kind of brainstorm with our technology partners and come up with a technology demonstration on your part, on your process, so that you can see how it can benefit you directly. And then if you find that to be useful and you want to go towards adoption, we do have both grant money available for you to onboard the technology. We have two different pots of money there, which we'll go over that in a moment. But then we also help with, on the engineering side, we provide that support. We're there on site with you. We will help to develop the process. We'll come on site, help you install the pieces of technologies and help you use it in an appropriate way. And then we follow that up with technology training. So we hold regular training events here at CCAT. Always check the website. There's always something going on. You're going to hear more from Eileen about some of the upcoming workshops here in a moment.
Great. Thank you, Nasir. Thank you, everybody. And I'm just going to really quickly go over some of these next couple of slides. We will also provide them as a follow-up, not only to everybody who's here in person, but to those of you who are online. So thanks, Nasir, and to all of the panelists, to Ron and Jackie for your comments earlier, and Walker for helping us coordinate this activity, and Shell for all her support. Money for manufacturing grants that you're seeing pictured here reference funding that CCAT has to administer across the state to Connecticut employers who are qualified to take advantage of these programs. And there on the left-hand side of the slide there, you'll see technology grants that pertain to Syrian cyber assistance support for you to embrace or to have outside cybersecurity assessments performed for your operation. The IoT integration voucher program is going to be replaced by a new program we have coming up that's $25,000 in terms of helping support implementation of smart manufacturing processes. The Manufacturing Innovation Fund is a up to $100,000 lifetime grant for bringing on new capital equipment. That one is restricted to companies that are 100 people and less. All of these other grants are for organizations that are 300 Connecticut employees and less. And then on the right-hand side, you see references to some workforce programs. So CCAT is administering funding for reimbursements for apprenticeships And those could be for up to 4 apprentices running at any given period of time. So truly it's $15,000 over the life of a 2-year internship. Or if you have 4 people simultaneously, it's $30,000 a year to offset your wages, your costs of having people on board in your organization. They have to have a structured apprenticeship training plan. There has to be pre-approvals by Connecticut's Department of Labor's Office of Apprenticeships, as well as the person needs to be signed up under that same application. And again, all of these workforce programs, they are reimbursements versus the technology grants. You have to sign up and be approved before you make a commitment to any of the capital equipment, software, or the Syrier cyber security assessments and trainings. For incumbent worker training, that's up to $50,000 to assist with upskill training current workers. Largely, that's to help with offsetting the cost, and could be offsetting the cost, to Ann's question, of bringing model-based definition on board and having an outside vendor come in and help those people. You could get $50,000 for your company to do that. So bingo, there's the answer to that question. And then the manufacturing internship program has to do with college interns and summer internships. And it not only includes engineering interns, for whom each individual company of less than 300 employees could be eligible for up to $7,000 in matching wage subsidies for qualified engineering interns. But the internship program is a series of events and tours and professional networking opportunities, professional development opportunities for college interns who are entering the manufacturing space. It could be a marketing intern. It could be a finance intern. It could be a computer science student helping bring on model-based definition to an operation. But it's a fabulous program. Last year we had a small cohort. This year we have much larger plans underway. Jackie leads that and I help implement it, and it's a ton of fun, and it's going to be a great, exciting program that will really help us do what Paul Lavoie refers to as helping those who learn in Connecticut, earn in Connecticut, and find that there's a lot of reasons that maybe they were born here, their parents live here, but they want to stay here too. So skipping forward to my next slide, the coming soon programs. The first listed there, Innovation Voucher Program, that's a slight lift. That reimbursement will be lifting up to 25K max for Innovation Voucher Program and adoption of Industry 4.0 digital solutions. And then there's newer programs, or a renewal of a program, $20,000 for additive manufacturing hardware, software, and third-party support. That's there will be 20 of those awarded, and then there will be 6 new awards of up to $100,000 each for a much larger acquisition and installation of new additive equipment. So really exciting. Please be sure to not only tell the membership base, Walker, but any associates, friends, and you as vendors, think about the application of some of these funds and what you are promoting and selling to your operation, to your customer base. On a workforce side, just to quickly mention, CCAT has for a number of years, over 10 years, led an industry-led employer voice organization, a network of employers who group together to talk about challenges and what are they going to do and share best practices to overcome them. That's had funding from the National Fund for Workforce Solutions. Our focus in the next year is more on training pathways for next gen, business development, and job quality. And that not only services the greater Hartford market and recognized as a North Central Connecticut regional sector partnership, but also provides services and support across the state. Career Connect, or RevUp, is a program that's sponsored under a federal funding that came to Connecticut under the leadership of Kelly Valeries. And RevUp is a program to help upskill workers in more advanced technologies. So robotics, automation, that program will help offset those costs and provide free training. There's a lot more details, and our website is about to be live very soon. And then Maker Multipliers is a very special website that celebrates champions that are young rising professionals representing a variety of manufacturing industries. And it's a platform that's not only used to showcase their stories and to inspire next gen, but also used by educators to showcase different career path options to students. Upcoming events, like Nasir said, if you follow us, both on social as well as just keeping an eye on ccat.us/events on an ongoing basis. We have great opportunities for you to participate or bring other colleagues and peers. Metal 3D printing will be the focus of a half-day forum on May 24th. Then we'll be talking about manufacturing variability with AI-informed digital twin on June 7th. That's 8 to 2. Both of those events are also available hybrid. So if you can't come in person, you can participate remotely. And then the Stratasys Mobile Showroom mobile bus will be here on June 7th as well, the same time as our digital twin event. And then NXCAM Swish will be providing some NXCAM fundamentals training. It's a paid training. The details on that are being finalized, but we could have up to $1,000 offset for qualified participants in that program as well. And then we have an open community tour on June 14th. And we regularly try to have those every quarter, but we will also do specialized targeted tours on request. Thank you. So you had a lot of information shared today. There's some of our contact information there. We will send a survey to those of you who've been participating remotely, as well as send a follow-up to all of you who've been here in person. And Nasir, do you want to make any final comments? We're sorry the remote audience couldn't be here for lunch and the great tour or demo that I hear we're going to have following as well. But thank you all.
Thanks, Eileen. Yeah, just wanted to close out by saying, again, thank you for being here, taking the time out of your busy schedules to be with us today. Please consider CCAT as your applied R&D lab. We're here funded by the state and federal government to provide a service to you. We're actively researching, seeing what kinds of technologies are out there. Technologies that you can use today, existing technologies that you can adopt immediately. We do test them out, put them through the ringer, if you will. We see the things that work, the things that don't work. We work with our technology providers. Sometimes we help to link to different companies that may otherwise not have been communicating before to come up with for the purpose of coming up with a viable solution. And so when you come to us, think of us as again, as I said, as your lab, where we can provide a solution. We have the technologies here that we can demonstrate on your particular parts and processes. So with that, we do have lunch available. It's going to be back here against the wall. And we have our partners, Scalable Robotics. Over in the back, you saw when you walked over in the Atom Lab side, the additive flex cell. They're going to be doing a demonstration there. So I invite you to get your lunch and feel free to walk over there and see the demonstration. Thank you again.